Hey y'all, today we are going to move into solving this behemoth. We're going to solve this truss. So, it's a long process. It's a lot of showing your work. You need to make sure you draw everything out, especially in your E and B. It's okay to take breaks. It's okay to break it into chunks. So take a deep breath. We got this. And I'm going to walk you through how we do this. So just like we've been doing with those simple beams, we have to start by making this a free body diagram because we have a roller, we have a pin. Okay. So we replace our pin with our two reactionary forces, RAX and RAY. We replace our roller with one reactionary force, RCY. Now we have to do some math to figure out if we can solve this truss. It's simple math though. We have to figure out if this is what is called statically determinant. Statically determinant is this equation right here. 2J equals M plus R. 2 times the number of joints equals the number of members plus the number of reactionary forces. So the way that looks on this truss is each of these little black dots that has a circle around it is a joint. Typically we label them with letters, so that helps you out. So we have 4 joints in this truss, A, B, C, and D. Each one of these rectangles, each one of these sections is a member. We have 5 members. The tricky part is notice this really long rectangle down at the bottom is actually 2 different members because it's broken up by joint D. It's not 1, it's 2 different members. So we have 5 members total. And then we have 3 reactionary forces, RAX, RAY, and RCY. So we look at 4 joints, 5 members, 3 reactionary forces. 2 times 4 equals 5 plus 3. So 8 equals 8. And that's true. So that means this is a statically determinate truss, so we can move forward with solving it. Our first step when solving this truss is exactly the same as with our simple beams. We have to find RAX, RAY, and RCY. So, how did we do that last time? We used some of the moments has to equal 0, some of the forces in the y direction has to equal 0, and some of the forces in the x direction has to equal 0. So, let's start with our sum of the moments, just like normal. Remember, we do the moment around the pin. So we're solving for RCY here. We're looking for the moment around pin at joint A. So we're holding that joint in one place and everything else is causing it to rotate. We have a moment at D because there's a force and it's a distance away from A. There's a force and it's a distance away from A. And there's a moment at C because there's a force and it's a distance away from A. There's nothing at B. There's no force directly at B right now, so we don't have to worry about that joint. And since the 2 forces are at A, 0 times anything, since there's 0 distance away from A, equals 0. So finding the moment at D, remember moment equals force times distance perpendicular. Our force is 2 tons. And remember, 1 ton is 2,000 pounds. So quickly converting those units from tons to pounds, we get 4,000 pounds times 15 feet, because as we see from our drawing, it is 15 feet between point A and point D. We get a moment of negative 60,000 foot-pounds. Negative because it's causing a clockwise rotation. And the moment at C equals our force, RCY, which we don't know yet, times our distance, which is 15 feet from A to D and 20 feet from D to C. So we add those two together to get 35 feet total. So we sub in what we know into our equation, move that 60,000 foot-pounds to the other side of the equation to get rid of the negative, divide by 35 feet to get RCY on its own, and we are left with RCY being 1,714.29 yada 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 pounds. So I don't take up 1.5 million decimal places and too much space on the PowerPoint in this video. I'm not going to write everything out, but remember, we don't round until the very end typically, so we don't skew our answers, okay? Now, we update our free body diagram. We have our force at D in the y direction. We have RCY. Now let's solve for RAY. Let's solve for that vector using sum of the forces in the y direction has to equal 0. So RAY plus FDY plus RCY has to equal 0. So RAY we don't know, plus negative 4,000 pounds, because remember, 2 tons is 4,000 pounds. We did that conversion earlier, and it's going in the negative y direction, plus RCY, which is 1,714.29 pounds. Again, unrounded. I'm just not going to say every single decimal place. We simplify, we're left with negative 2,285.71, yada, 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 yada. Move that to the other side, and we get RAY on its own. So RAY equals 2,285.71 pounds. Now we just need to solve for RAX. Sum of the forces in the x direction has to equal 0. Well, RAX is the only force in the x direction, so it has to equal 0. So the next thing is we have to solve this truss using what's called the method of joints. So we look at each joint, and we have to solve each member to figure out what forces are going on it. One of the things we need to be able to do that is these angles at joint A and joint C. Thankfully, we can get those angles with some basic trigonometry. We have a distance from A to D. We have a distance from A to C. So we can find these angles by using some basic trigonometry, using the inverse tangent, since we have our opposite and our adjacent. We just have to make sure we put them in the right place. When we do that trigonometry, we've gone over it a couple times, so I'm not going to go super in-depth here with it. We get that the angle at A is 45 degrees, and the angle at C is roughly 37 degrees. So, with the method of joints, we have to make some assumptions for all of our stuff to work. Our assumptions are that all members are in tension. Any negative number that we get when we calculate these forces, so you notice how all of my members now, there's a force between A and B, there's a force between B and D, there's a force between A and D, there's a force between C and D, and there's a force between B and C. If I get a negative number when I solve for any of those, that lets me know that my assumption was wrong, and this is compression, not tension. When that happens, we have to update our free body diagram and adjust which way our arrow's pointing, okay? I know that sounds confusing. Seeing as we walk through it here is going to make a lot more sense, I promise. So the first thing we do is we change from those rectangles to each joint being an independent free body diagram. So everything's in tension, so that means it is going away from our joint, outside of RCY and RAY, since we already found those vectors from before. So when I do this, I almost always start at the pin. We always want to start where there's the least amount of unknowns. So here, when we're inside and just solving for each joint's free body diagram, we don't get to use sum of the moments anymore. We only have sum of the forces in the y direction and sum of the forces in the x direction. And to get some of those values, we have to use sine, cosine, and tangent. So for instance, we're going to solve for FAB first, this orange vector. Why did I choose FAB? Well, I have RAX, and I have RAY, and I have my angle, theta at A. I want to look for the least amount of unknowns. Well, I don't know FAD, which is in the x direction, and I don't know FAB, which has an x and y component because it's going up and to the right. But FAB has a y component, and I know RAY, so I know those two added together have to equal 0. So what I do first is I solve for that FAB y component in the y direction. So I plug in that I know RAY is 2,285.71 pounds, and that's positive because it's going up. So that means FABY has to be negative 2,285.71 pounds for things to cancel out and equal 0. After I know what FABY equals, I have my angle and this leg of my triangle. Now with that leg of my triangle, I know that is opposite my angle. So I'm going to use sine since I'm solving for my hypotenuse. So sine of 45 equals opposite over hypotenuse, FABY over FAB. When I rearrange the equation to get FAB on its own, I multiply by FAB and divide by sine of 45. So I get FAB equals FABY divided by sine of 45. Since we already found that FABY has to be negative 2,285.71 pounds, we plug that in. Then we just have to plug this into our calculator. When we get that FAB has to be negative 3,232.48 and some other decimals pounds. Remember, a negative number means that this is in compression. So when it's in compression, we have to flip this arrow. Since FABY has to be going down, the only way this can still be going down along this path is to get this arrowhead on this end. So we physically flip which direction our arrowhead is pointing for our vector. Now that we have FAB, we update it in our free body diagram, and I put a little C so that way we remember that we had to flip it because it's in compression, not tension. That always helps me when I'm going back and using this value in other equations. Since we found FAB in here at joint A, we don't have to find it at joint B. So now that we found it, we're done. We don't have to touch FAB again. So now we're going to solve for FAD. FAD is in the x direction, so we have to use our sum of the forces in the x direction. But we didn't calculate what FAB in the x direction would be yet, and it clearly has an x component since it's diagonal. So the first thing we need to do is find that FABX, which we know FABX would be right here over FAD. So that is the adjacent side. And we found our hypotenuse. So cosine of 45 times our hypotenuse gives us FAB in the x direction. So when you plug that into your calculator, FAB in the x direction equals 2,285.71 pounds. Now, Mr. Bolin, why is that negative? That's letting us know that FABX has to go to the left in the negative x direction, which makes sense since our arrowhead is down and to the left for our sense. So now that we have all of the x components figured out, we can use sum of the forces in the x direction to figure out FAD. So I know RAX, I know FABX, and we're looking for FAD. We plug in what we know. RAX is 0, FABX is negative 2,285.71 pounds. We move things to the other side to get FAD on its own, and FAD has to be 2,285.71 pounds, and that's positive, which means our assumption of tension was true. So now we need to update our free body diagram with that. So remember, like I said, once you find a member in one joint free body diagram, you have it for the whole truss. So since we just found FAD, we can use it at joint D here to solve for FBD and FCD. Now these are really, really straightforward since they're just vertical and horizontal arrows. So solving for FCD, sum of the forces in the x direction has to equal 0. That means FAD plus FCD has to equal 0. And we know FAD is 2,285.71 pounds. Wait, Mr. Bolin, why is it negative now? Look at it in this free body diagram. In this free body diagram at joint D, it is going in the negative x direction. So we have to account for that in our math. Move that to the other side to solve for FCD, and we get that FCD is 2,285.71 pounds in the positive x direction. So it is under tension. And then solving for BD, sum of the forces in the y direction has to be 0. So FBD plus FDY has to equal 0. We know that FDY is 4,000 pounds, and it is going in the negative y direction, so it has to be negative 4,000 pounds. So move it to the other side, and FBD has to equal 4,000 pounds. So it's in tension because it's positive. Easiest joint in the whole truss. Now we've solved for everything in our truss but FBC. Remember, we updated our free body diagram, so FCD equals 2,285.71 pounds of tension, and we have our RCY value. So now we can solve for FBC using this angle and the values we found. So I like to do this in the sum of the forces in the y direction, just because it's almost identical to solving for FAB, but you can also do this by solving for it in the x direction if you'd rather. So I do RCY plus FBCY has to equal 0, because remember, we have to find the component and then find FBC. So I know that RCY is 1,714.29 pounds. So that means to find FBCY on its own, FBCY has to be negative 1,714.29 pounds. So now that we know what FBCY is, we can use our trigonometry to solve for FBC. So remember, we have a y component and an x component. So that y component is opposite my angle, and I'm looking for the hypotenuse, so I'm going to use sine. I'm solving for FBC, so I need to rearrange my equation to get FBC on its own. Then I need to plug in what I know for FBCY. Remember, we found that as negative 1,714.29 pounds. When I plug that into my calculator, I get that FBC is negative 2,848.53 and some change pounds. So since that's a negative number, it's compression, and we have to update our free body diagram again. So we have to flip that arrowhead for FBC. So when we get to the end, this is what our updated free body diagram should look like. We need to have a magnitude for each vector, whether it's under compression or tension, and we need to make sure that our vector arrowheads are pointing in the correct direction. Remember, if it's tension, it should be going away from the joint. If it's compression, the arrowhead should be going into the joint. So make sure as you're doing these in your ENB, I would strongly recommend you do them in pencil first, since we may need to flip arrowheads in tension versus compression. But all in all, that's it. You're done. That is one full truss problem. As you can see, it's not terrible. It's just lengthy because we have to go through each joint, and it's repetitive. Notice I didn't have to touch joint B at all outside of updating arrowheads because I found FAB at joint A, FBD at joint D, and FBC at joint C. So the last step is I want you to practice with this truss. So make sure you copy it down, go through all these steps that we did, and solve for the complete free body diagram for this truss. Let me know if you have any questions. Y'all got this. You're prepared. You're smart. You can handle it. Trusses are not that scary. I believe in you.